Have you ever wondered what would happen if a star exploded and hit our Earth? No? Okay. Well, today we're gonna see what happens if that happened. I guess with this video by Veritasium. Veritasium. Anyways, and this video is called "What Happens If a Star Explodes Near the Earth." So let's get to it.
What would happen if a star exploded near the Earth? Well, the nearest star to Earth, of course, is the Sun, and it is not going to explode. But if it had 8 times the mass, then it would go supernova at the end of its life. So what would that look like? Well, as noted by XKCD, if you held up a hydrogen bomb right to your eyeball and detonated it, that explosion would still be 1 billion times less bright than watching the Sun go supernova from Earth.
That's crazy.
That's how insanely powerful supernova explosions are. They are the biggest explosions in the universe.
Wow.
When we see supernovae in other galaxies, they are brighter than the combined light of hundreds of billions of stars. So bright, in fact, that they appear to come out of nowhere. On the 8th of October 1604, the astronomer Johannes Kepler looked up into the night sky and noticed a bright star he had never seen before. It was brighter than all the other stars in the sky, and about as bright as the planet Jupiter. On moonless nights, it was bright enough to cast a shadow. Kepler published his observations of this star in a book called De Stella Nova, which means about a new star in Latin. Kepler thought he was witnessing the birth of a new star, but it was actually a star's violent death. Over the following year and a half, the light faded until it was no longer visible. But the name stuck. Even once we learned what was really happening in the 1930s, the violent final explosion for stars between about 8 and 30 solar masses has been called a supernova. But how exactly a star explodes is not what most people think. For most of a star's life, it exists in a stable balance. In its core, it fuses lighter elements together to make heavier ones, and in the process, it converts a small amount of matter into energy. This energy is really what keeps the star from collapsing in on itself. Gravity compresses the star, but that force is counteracted by the pressure generated by the movement of particles inside the star, and by the pressure of photons released by fusion. So, in effect, stars are propped up by their own light. If the rate of fusion drops at the center of the star, the temperature and the pressure decrease. Gravity starts winning, compressing the star. But this increases the temperature and pressure in the core, which increases the rate of fusion. It's a stable, self-regulating system. But there's a problem. Stars have a finite amount of fuel, which over time gets used up. Our Sun is about 5 billion years into its 10 billion year lifespan. There are stars dozens of times more massive than the Sun, which you would think would live much longer, but they actually use up their nuclear fuel faster. A star 20 times the mass of our Sun has a lifespan of just 10 million years, and more massive stars burn hotter and even brighter, but for much shorter lives. For 90% the life of a star, the core is only hot enough to fuse hydrogen into helium. And when the hydrogen runs out, fusion slows, gravity compresses the core, and its temperature increases to 200 million degrees, at which point helium fuses into carbon. There's enough helium to power the star for around 1 million years, but as the helium runs out, the core is again compressed and heated. Carbon starts fusing into neon, which lasts about 1,000 years, and then neon fuses into oxygen for a few more years, then oxygen to silicon for a few months, and at 2.5 billion degrees, silicon fuses into nickel, which decays into iron. Now, at the heart of this giant star, there is an iron core building that's only a few thousand kilometers across. Iron is where this pattern stops. instead of liberating energy as it fuses into heavier elements, it actually requires energy. Iron is the most stable element, so it actually takes energy both to fuse it into heavier elements and to break it down into lighter ones. Both fusion and fission reactions ultimately end up at iron. The iron core grows, but the crush of gravity becomes greater and greater as the rate of fusion drops. When the iron core is about 1.4 times the mass of our Sun, which is known as the Chandrasekhar limit, the pull of gravity is so strong that something totally wild happens. Quantum mechanics takes over. Electrons run out of room to move, and they're forced into their lowest energy states. They then become absorbed by the protons in the nucleus. In this process, the protons turn into neutrons and release neutrinos. With the electrons gone, the core collapses, and fast, at about 25% the speed of light. So what used to be a ball of iron 3,000 kilometers in diameter becomes a ball of neutrons just 30 kilometers across. Essentially, it's a neutron star. With no outward pressure to hold it up, the rest of the star caves in, also falling at a quarter the speed of light. It hits the neutron star and bounces off, creating a huge pressure wave. But this kinetic energy isn't quite enough to start a supernova explosion. No, the thing that really kicks it off is the humble neutrino. Now, I normally think of neutrinos as particles that do basically nothing. I mean, they interact so rarely with matter that right now, there are 100 trillion neutrinos passing through your body per second. It would take a light year of lead just to give you a 50-50 chance of stopping a neutrino. And that's because they interact only through gravity and the weak force. But in a supernova, when the electrons are captured by the protons, an unbelievable number of neutrinos is released, around 10 to the 58. You would think they would just fly off at nearly the speed of light, but the core of a supernova is incredibly dense, about 10 trillion times more dense than lead. And as a result, it traps some of those neutrinos and captures their energy. And this is what makes a star go supernova. A particle that is millions of times less massive than an electron, that barely interacts with anything, is responsible for some of the largest explosions in the universe. In that explosion, only 1/100th of 1% of the energy is released as electromagnetic radiation, the light that we can see. Even then, supernovae have enough energy to outshine a whole galaxy. About 1% of the energy is released as the kinetic energy of the exploding matter, but the vast majority of the energy is released in the form of neutrinos. And neutrinos are actually the first signal we detect from supernovae. And that's because after they're generated in the core, they can escape before the shock wave reaches the surface, where the light that we see is generated. So neutrinos can arrive on Earth hours before the photons, giving astronomers a chance to aim their telescopes at the right part of the sky. I actually used to work at a neutrino observatory back in college, and I would work the graveyard shift between midnight and 8 a.m. So if I detected a really big increase in the neutrino flux during my shift, it was my job to call and wake up scientists so they could go look out for a supernova. Now that never actually happened, but we did have some close calls. Now I need to clarify a couple things. First, not all really massive stars explode. As they collapse, some form black holes instead, which means they do not go supernova. And second, there's another way to make a supernova. Sometimes a white dwarf star, which is incredibly dense, pulls matter off a nearby star. And when its mass reaches that Chandrasekhar limit of 1.4 solar masses, the white dwarf collapses, creating a supernova. This is actually the type of supernova that Kepler saw in 1604, a supernova 20,000 light years from Earth.
That's crazy
Now,
how far.
because the shocks are asymmetric, supernova explain neutron stars that can move really fast. There's a neutron star we've observed with the velocity
That looks
of
so weird.
1,600 kilometers per second. And we think that was caused by a very asymmetric supernova explosion, sent it shooting off in the other direction. Despite only recently learning about how supernovae work, humans have been observing them for thousands of years. Ancient Indian, Chinese, Arabic, and European astronomers all observed supernovae, but they are quite rare. In a galaxy like our Milky Way, consisting of 100 billion stars, there are only about 1 or 2 supernovae per century. A particularly amazing example is the supernova of 1054, when the light of a supernova 6,500 light years away reached the Earth and was recorded by Chinese astronomers. If we look to where that supernova was recorded, we see the Crab Nebula. It is a giant remnant of radioactive matter left behind by the explosion. In the 1,000 years since the explosion, the remnant has grown to 11 light years in diameter.
Looks like a brain,
Supernovas produce a lot of cosmic rays.
a brain
Cosmic rays are actually
scan
particles,
thing.
mainly protons and helium nuclei, and they travel out at very, very nearly the speed of light. They have a tremendous amount of energy. So, at what distance could a supernova cause problems for life on Earth? The closest stars to us, besides the Sun, are the 3 stars in Alpha Centauri. They are 4.4 light years away. But stars do move around, and on average, a star gets within 1 light year of Earth every 500,000 years. So, what would happen if such a star went off?
That's crazy.
Yeah, so within a light year, you're easily within a danger distance from just the kinetic energy. So I think even at that distance, you're looking at possibly blowing the atmosphere off.
But we would also have other problems to worry about. Supernovae create conditions that are hot enough to fuse elements heavier than iron. In the months after the explosion, these elements undergo radioactive decay, producing gamma rays and cosmic rays. Less than 0.1% of the energy produced by a supernova is emitted as gamma rays from these radioactive decays, but even this tiny percentage can be dangerous. At a few light years from a supernova, the radiation could be deadly, though most of it would be blocked by our atmosphere. Now, the Earth is protected from solar and cosmic radiation by our atmosphere, and specifically by ozone molecules, the 3 oxygen atoms bonded together. But high-energy cosmic rays from supernovae can come down and break apart nitrogen molecules in the atmosphere. And then these bond with oxygen atoms, which can then break apart ozone. And so we can lose a lot of our ozone if there's too many cosmic rays coming from supernova events, and that can expose us to all kinds of dangerous radiation coming in from space.
Damn.
We actually see an increase in atmospheric NO3 concentrations coinciding with supernova explosions. A supernova within 30 light years is rare, only happening maybe once every 1.5 billion years or so. But a recent article suggests supernovae could be lethal all the way out to 150 light years away, and so those would be much more common. We actually have evidence for a supernova that went off 150 light years from Earth 2.6 million years ago. It would have been seen by our early human ancestors, like Australopithecus. And we know this because there are elements present on Earth that could only have been deposited by a recent supernova. In sedimentary rocks at the bottom of the Pacific Ocean, scientists have found traces of iron-60 in a layer that was deposited 2.6 million years ago. Iron-60 is an isotope of iron with 4 more neutrons than the most common type of iron. Iron-60 is really hard to make. Our sun doesn't make it, nor is it produced basically anywhere else in the solar system. Iron-60 is made basically exclusively in supernova explosions. And iron-60 is radioactive. It has a half-life
Crazy how they would know that.
2.6 million years. So every 2.6 million years, half of the sample decays into cobalt-60. So all of the iron-60 that was around during the formation of the Earth 4.5 billion years ago has definitely decayed. So the iron-60 that the scientists measure is proof of a recent supernova. Scientists also measured trace amounts of manganese-53 in the same sediments, giving further evidence supporting the idea that recently there was an explosion of a nearby supernova. The supernova that happened 2.6 million years ago wasn't catastrophic for our ancestors, but some researchers hypothesized that it could be related to the mass extinction which is seen at the Pliocene-Pleistocene boundary in the fossil record around the same time.
Alright, I'm gonna have to stop here. This is doing too much. Like, this is cool and all, but this is crazy.
The idea is that
Like,
cosmic rays
I'm
from
not.
short
I
out
feel so
particles
stupid.
and